The third conic section we are going to study is called a hyperbola. You have probably heard of, I know you've heard of circles. You probably have heard of ellipses. You maybe haven't had that name, but you've certainly seen things like that. Hyperbolas are a little less common in your study of mathematics, so you may or may not have seen those. This is the conic section that slices perpendicular to the base of the cone, and it crosses both the top and that bottom cone, and it'll give us a picture like what we see here in this, where that slice goes, across the two cones there. We define a hyperbola as the set of points in a plane such that the difference between the distance between the distances from two fixed points is constant. On the ellipse, we added, like in this picture, d1 plus d2 gave us an ellipse. That was constant. Here we are going to do d1 minus d2, and that is constant. With a hyperbola, we need to be able to determine the vertices, the foci, and the asymptotes of the hyperbola. The reason we need those is because that will help us solve some of these applications involving hyperbolas. We also want to be able to write the equation of a hyperbola and graph hyperbolas. Again, all of that gives us a better understanding of these applications involving hyperbolas. Notice here that the standard form of the equation of a hyperbola with center at the origin is very similar to what we saw with an ellipse. The main difference here is we have a minus sign instead of a plus sign. That is because our definition talks about the difference of these distances. By the way, there is a typed up sort of proof of where this equation comes from located in the D2L shell as a reference for you for, okay, why is that equation what it is? Here, I don't have it typed up for the hyperbola, but it's going to be very similar. It's just the difference instead of the addition that we saw with the ellipse. Because subtraction is not commutative, meaning when you switch the order you get different results, we have to have two different options here. With the ellipse, it didn't really matter. Let me go back up here. It doesn't really matter in this case. Oh gosh, how did I miss my plus sign there? It doesn't really matter if you have the x squared or the y squared first, right? We could certainly switch these two terms and we still get the same result. That's not true with the hyperbola. It is important that you know which comes first. Just like with the ellipse, if the center is not at the origin, we're going to have a shift, horizontal and vertical translation, so we'll have an x minus h and a y minus k in there. Let's take a look. We could have a horizontal hyperbola where the parts of the hyperbola sort of curve horizontally, right? They kind of open up to the sides. Vertical hyperbolas where these parts of the hyperbola sort of open up to the top and the bottom. We do have asymptotes in a hyperbola. These will approach a asymptote. The points here are called the vertices, so there's actually only two of them. Unlike the ellipse where we had four, we had two on the major axis and two on the minor axis. The center is not part of the graph. These points right here are the only points on the graph. The vertices are on the graph, but the center is not actually on the graph, similar to the ellipse, right? Or the circle. So we call this the transverse axis, the one that sort of cuts across it. And that's what we're going to be focusing on. Notice up here, if the positive term is the x term, we have the positive in front of this x term. It is the horizontal hyperbola. It opens up to the sides. The negative on the y makes this horizontal. Here, The positive on the y makes it vertical. So that's kind of how I remember that, is this what tells us which way it opens up. The center is halfway between the vertices. It will be HK in this formula, whichever format it's in. Even if these two are switched, it's still the number subtracted from the x is still the x coordinate of the center. Length of the semi-transverse axis, or the, so semi-transverse, we're talking about half of that. So the A here in both of these situations is this distance, or here it's this distance. B would be the length of the semi-conjugate axis, which would be that's half of it, okay? That's this and this. The easiest way to do this really is to go out these distances and sort of create this rectangle here. That helps us find our asymptotes. That helps us find how what the sort of width of this graph really looks like. The focus for the hyperbola is actually on the outside. The hyperbola sort of curves around the focus. That makes it the biggest number. The C will be the biggest number. And so, oh yeah, here I did write it. So because of that, remember we could rewrite this as c squared equals a squared plus b squared. So now with the hyperbola, the c squared is by itself because it is the biggest number, the distance to the focus. Same thing here. Don't memorize this, but be able to use it. We'll talk about finding the asymptotes in the context of an application. You're writing equations of lines, so use what you know about writing equations of lines for that. I do not memorize this. Let's look at it. Here we have x squared over 9 minus y squared over 49 equals 1. It looks a little strange there, doesn't it? The spacing seems a little off. Okay, first thing I notice, center is at the origin because there's nothing added or subtracted inside those x squared and y squared. So here. Then I notice that this sort of opens left and right because the x is first here. I go out a distance of 3, the square root of that 9, 1, 2, 3. That's going to be a vertex, 1, 2, 3. That's going to be a vertex. I also go out a distance of 7 from the center vertically, 1, 2, 3, 4, 5, 6, 7. Here, that point's not going to be on the function, or the hyperbola. These are not functions. They don't pass the vertical line test. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6, 7. So here. What I'm using that for is to create this box. I'm going to dash in this rectangular shape here that goes out to the 7, goes out to the actual vertices. The reason I like that is because that allows me to graph my asymptotes. The asymptotes are the diagonals of this. Okay. So I'm going to actually go ahead and graph my hyperbola from this. This is a pretty wide hyperbola here. This approaches these asymptotes from the vertex there, vertices, the two of them. It's got this curving shape approaching the asymptotes. So we've done the sketch the graph part. Let's find the foci, the vertices, and the equations of the asymptotes. The vertices we already have at 3, 0 and negative 3, 0. Remember that hyperbolas sort of curve around the foci, so it's somewhere out here and somewhere out here where that distance is the biggest distance. So it's going to be by itself in this a squared plus b squared equals c squared thing. 9 and 49 are the other two numbers from this denominator, the a squared and the b squared. 58 is c squared, so c is plus or minus root 58. That doesn't simplify because that's 2 times 29. Both of those are prime numbers, so they don't simplify. That is, however, approximately, it's going to be somewhere between 7 and 8, because 58 is between 49 and 64. Square root of 58 is approximately 7.6. I just want that so that I can graph them. 3, 4, 5, 6, 7.6. The foci would be way out here. 4, 5, 6, 7, 7.6. Those ordered pairs, because it asks you to find those, along the x-axis, a distance of root 58 would be from the center, which is 0, 0. So vertices, foci, and we need the equations of the asymptotes. These are actually not too bad when the center is at the origin, because remember, if you're looking at y equals mx plus b, both of these lines go through the origin, so b will be 0. That's the y-intercept of these lines. The slope, that's why I like this rectangle. Rise over run, right? In this case, the rise is 7, the run is 3. So we get 7/3 x. The other one is the same, but it's the negative. So often you will just put the plus or minus in here. Y equals, y equals plus or minus 7/3 x. The 7/3, positive 7/3 is the increasing line. The negative 7/3 is the decreasing line. I really like the rectangle to help us with that. This was particularly, I would say, easy because the center is at the origin, so I know that b is 0. But if it's not, you would want to use y minus y1 is m times x minus x1, where you're using the center. So you'd use the h and the k here, because that center will always be on the equations of those lines. Okay, let's try another one. This one is not centered at the origin, so we are going to need a little bit more work here. Just like with the ellipse, we need it equal to 0. So we are going to divide both sides of this equation by 16. Y minus 3 squared over 4 minus x plus 1 squared over 16 will equal 1. First, I note that the center is -1, 3. Be careful here. It might be easy to say 3, -1. The x coordinate of the center goes with the x. Because the y is first, it opens, put quotes around that, up and down. It's this vertical hyperbola. Let's graph what we have here. -1, 3 is here. My vertices are going to be above and below that because it opens up and down. Specifically, 2 spaces above, 2 spaces below. That impacts the y coordinate, right? Add 2, and subtract 2. So negative 1, 1 and negative 1, 5 will be the vertices. I'm going to do the same thing. I went 2 because that's the square root of this 4, right? I'm going to do the same thing here. Square root of 4 is, square root of 16 is 4. So horizontally from the center, I'm going to go out 4 spaces. 1, 2, 3, 4. That doesn't help me find the a point on the hyperbola, but it helps me complete my rectangle, which is really helpful in finding these. Now my asymptotes are here. And here. So I'm going to have this picture through the vertices approaching the asymptotes. Nice curve here. While we're talking about the asymptotes, let's find the equation of them. The slope of the asymptotes, we need the slope to be able to write the equation, right? Rise 2, run 4, or 1/2. Rise 2, run negative 4, so it'll be negative 1/2, right? I need a point that is on the lines. The center will always be on the lines. So I'm using the center. Y minus 3 equals plus or minus 1/2 times x minus negative 1 gives me plus 1. Those will be the equations, 2 equations of my 2 different asymptotes. Don't try to memorize this up here, okay? This plus k was added over, so if you wanted to do that, you would add 3 to both sides, right? If you wanted to keep in line with what's up there. Plus or minus 1/2 times x plus 1 plus 3. I really don't want you to memorize what's up there, though, because you know how to write the equation of a line. There's no need to memorize more information than you already have. So write the equation of a line using that point slope form, plugging in the center because it is on both lines, and use rise over run to find the slope in that rectangle. Last thing I think we need here is these focal points, right? We have the vertices, we have the asymptotes, we still need that. Remember, they're going to be out here somewhere. They are the biggest distance in the hyperbola. 4 is this distance squared. 16 is that horizontal distance squared. So c squared is 20. So c would be the square root of 20, or 2 root 5, technically plus or minus. From the center, we're going that distance, right? I want to approximate that just for the purposes of my graph. When I'm writing the coordinates, I do not want to approximate. It's approximately 4.5. From the center, I go down 1, 2, 3, 4.5. And I go up 1, 2, 3, 4.5. That will be where your focal points lie. Let's find the actual ordered pairs. If we're going up and down from the center, the x coordinate is not going to change from the center. From the 3, I am going up a distance of the square root of 20. So 3 plus root 20. I don't want to write that. I don't like root 20. It's not the most simplified. Let's call it 2 root 5. And then to go down, I need to subtract that distance of 2 root 5. So those are my focal points. Okay. We have done a lot of finding information about hyperbolas from different equations, right? I gave you the equation in both of these examples, and you found a bunch of information about it. Now we're going to go the other way. I should have given you a place to graph this just because it is much easier to do this by looking at a picture. If we have a vertex at 2, 0, that's here. The asymptotes are y equals 3/2 x. That tells me that the y-intercept is 0. The lines have to go through the origin. That means the center of this hyperbola is the origin. Rise 3/2. This will be my asymptote, and this will be the other asymptote here. Y equals 3/2 x and y equals negative 3/2 x. Well, because that point 2, 3 is on this line, that's what makes up my rectangle. Where this distance is 2 and this distance is 3. If my vertex is here, my parabola's open to the, not parabolas, they are not parabolas. My hyperbola opens to the side. It opens left and right. The value of that is knowing that my x will come first. Center of 0, and go in there, minus sign between them, equal to 1, and I just need to find my denominators. Under the x, from the center out to the vertex, is a distance of 2 squared. I have to square that distance, always, on all of these. Vertically, I go a distance of 3 squared. Simplifying this, I get x squared over 9 minus x squared over 4 minus y squared over 9. Until sometimes my brain thinks ahead. Sheesh. Okay, that's the equation of that hyperbola with those asymptotes and a vertex at 2, 0. I'm going to stop here before this video gets too long. We'll look at one more example and then we'll get into the applications of hyperbolas. You'll see some cool applications there when we come back.